my earlier video, I had discussed about mean value theorem, and today I will talk about Rolle's theorem. Actually, Rolle's theorem is special case of mean value theorem, and this theorem actually discovered by French mathematician Rolle. But at first I will recommend you, please see my earlier video, then today's video would be so easy. The statement of the Rolle's theorem is similar to mean value theorem. Suppose f be a function from closed interval ab to R, okay, and consider f is continuous on closed interval ab, and similar to mean value theorem, f is differentiable on the open interval ab, and function crosses here x-axis then again x-axis. That means here f of a equal to f of b, then there exists a point C in open interval AB such that f prime C equal to 0, where C be the any point between the open interval AB. That means here only difference here in Rolle's theorem, the slope of the secant line must be equal to 0, where for all C belongs to AB. This is only difference to mean value theorem, okay. And graph of the function is look like, consider this function, this is A and this is B, and this point is f of A and this point is also f of B. Notice f of A crosses x-axis and f of B also crosses x-axis. Then at the point C, the slope of the tangent would be 0. That means here f prime C equal to 0. This is the picture of Rolle's theorem, okay. And for Rolle's theorem, if f of x equal to f of A for all x belongs to closed interval AB, that implies function is constant function. And then this theorem is trivial, because when the function is constant, then always slope of the tangent means f prime C always will be 0. But when the function is not constant, then by extreme value theorem, it has either global maximum or global minimum. So it is a local maximum or minimum as well as, and global means just entire domain and local means some points in the some neighborhood. That means f prime of C must be equal to 0. This, just recall the Fermat's theorem. Consider f be a function AB to R and C be an arbitrary point between AB, and consider f is differentiable at C, and f of C is either maximum or minimum of the output. And we all of us know the maximum means f of C always greater than equal to fx for all x belongs to AB, and minimum means f of C always less than equal to fx for all x belongs to AB. And that conclusion gives f prime c equal to 0. Okay? Rolle's theorem similarly imply f be a function from closed interval ab to R, and f is continuous on closed interval ab, f is differentiable on ab. But here f of a equal to f of b. Then by Rolle's theorem there exists a c in AB such that f prime c equal to 0. Actually, the Fermat's theorem is a lemma of Rolle's theorem. Okay? In Rolle's theorem, when the function is constant, then derivative always equal to 0, it is obvious. But otherwise, the function should be up and down. That means the function should be monotony increasing or decreasing, or decreasing or increasing. It does not mean totally monotony increasing and totally monotony decreasing. It means after increase it will be decrease, or after decrease it will be increase. We all of us know when the function is increasing, then f prime x would be greater than 0, and when the function is decreasing, then f prime x would be less than 0, which I had proved in my earlier video by mean value theorem. Okay? And somewhere it will be cross 0. This is the sign of derivative which will be changed from positive to negative. Okay? And at this point the function has a either local minimum or local maximum. These hypotheses of Rolle's theorem are sufficient, not necessary. For conclusion, if the function is continuity in closed interval AB, differentiability in open interval AB, and if f of a equal to f of b, then that always imply f prime c equal to 0. If that means if these conditions are satisfied, then obviously f prime c equal to 0, it is guaranteed. But if the hypotheses are not met, then you may or may not reach the conclusion. Means if these conditions are not satisfied, then there exists some function where f prime c equal to 0, or there exists some function where f prime c not equal to 0. Okay? For example, consider this function fx equal to x square between the interval -2 to 1 and 3x minus 2 between the interval open interval 1 to 2. This is the graph of the function. Just think, this part is 3x minus 2 from the point open interval 1 to close interval 2, and from the point -2 to 1 the value is x square. Notice the function is continuous in overall the interval, but check the differentiability at the point 1, because here the break. If you calculate f prime 1 plus 0 when 1 goes to from right side, then the value would be 3. And if you calculate also f prime 1 minus 0, that means when 1 goes to from left side, then the value would be 2. That means the function is not differentiable. At the point x equal to 1. But notice f prime 0 equal to 0, because f prime x equal to f prime 0 equal to in this interval f prime x equal to 2x, and at the point 0 the value would be 0. That means here I have got 1.0 where the derivative of the function is 0. Let's say other different type of example. F of x equal to x in the interval 0 to 1 and 2 minus x in the interval 1 to 2. And notice this is the graph of this function. From the picture it is clear at the point 1 the function cannot be differentiable. Here between the open interval 0 to there exists no point such that the derivative does not vanishes. Okay, but I have seen in my earlier example this function also not differentiable but derivative vanishes at the point 0. Therefore, are you getting? The Rolle's theorem is not necessary condition. It is a sufficient condition. Now I will see some application of Rolle's theorem. Consider this example. The example tells using Rolle's theorem show that the equation, consider this equation, has exactly one real root in the closed interval 0, 1. I will prove this example by Rolle's theorem. And I will do this example by contradiction. Suppose fx equal to x to the power 13 plus 7x cube minus 5 equal to 0 has more than one root, one real root in the closed interval 0, 1. Okay. Here since I have considered there exists more than one root, that means there exists alpha beta such that f of alpha equal to 0 which is also equal to f of beta, where since here the interval closed interval 0, 1, that means alpha beta will be lies between the interval 0 and 1. 0 is strictly less than alpha, strictly less than beta, strictly less than 1. Okay. Then by Rolle's theorem, since f of alpha equal to f of beta equal to 0, by Rolle's theorem we can tell there exists C between alpha beta such that a prime C equal to 0 where for some C belongs to alpha beta. That means that imply just do derivative 13 C to the power 12 plus 21 C square equal to 0. But C lies between alpha beta. That means the value of C always greater than 0. Since C be any positive number, that means this quantity cannot be equal to 0 anywhere, since C is greater than 0. That means our assumption is a wrong assumption. We cannot tell there exists more than one real root. Okay. And notice here actually have used the intermediate value theorem, because f of 0 times f of 1 here less than 0. So by intermediate value theorem always we can tell there exists at least one root. Okay. There exists a shortcut trick. For at most one root you are going to use the Rolle's theorem. At most one roots mean it can have 2 or more than 2, or it must have at most 1 root. Okay? For this situation, you can use Rolle's theorem. But for exactly 1 root, you can use intermediate value theorem. And here you can show there cannot use the Rolle's theorem because there are not more than 1 root. Okay, the question, if given there exists certain number of root, then always will be used intermediate value theorem, and this is the shortcut trick. If you can remember this trick, then you will can easily find root of any equation. Okay, this is very important for any competitive exam also.